So we are going to start with the counter topic, and in this counter topic we are going to focus on the type of the counters, that is asynchronous and synchronous counters. Already we have started with this topic in the class. So here I will explain you how to design the counter, that is a 3-bit counter. Okay, so we have already studied the classification of counter on the basis of the counting direction, how it works on the basis of the clock provided to it, and the number of bits for which you are designing that counter. Okay, so if you classify it on the basis of counting direction, then it can be classified as up counter, down counter, or as a bidirectional counter. And if you are classifying it on the basis of the clock provided to the counter circuit, then it can be classified as asynchronous or synchronous counter. Okay, and on the basis of number of bits, that that means how many bit counter you are designing, that is n bit counter. So 2-bit, 3-bit, 4-bit, or 8, and so on. So it depends upon the counter you are designing for how many bits. So we are going to focus on the two types of counter, that is synchronous and asynchronous. So we are started with this topic in the class, that what is synchronous counter, what is asynchronous counter, and on the basis of clock, how do we differentiate them, right? So the clock provided to synchronous and asynchronous counter. If the clock is synchronous, if the clock provided to all the flip-flops at a time in one clock pulse, if all the flip-flops are getting activated, then we call it as a synchronous or a parallel counter. Means parallelly we are providing clock to the flip-flops. In a asynchronous counter, we are providing clock to only one flip-flop, and the second flip-flop is actually activated, or the clock for the second flip-flop is provided by the output of the previous one. Okay, so this is about the asynchronous counter. So asynchronous counter are also called as a ripple counter. Okay, so we know what actually a asynchronous counter is. Now in asynchronous counter, first we will see, I will just explain you how we can differentiate them from the synchronous counter, or what is main difference between synchronous and asynchronous. Okay, so in asynchronous counter, to design any counter, first we should know that how many bits you want to design a counter for, how many number of bits. Then from the bits you can find out what are the number of flip-flops required, and then you can find out what are the number of states from that counter. Okay, if I'm saying it is a 2-bit counter, for example, if it is a 2-bit counter, then the number of flip-flops required will be 2 flip-flops, because one flip-flop can store only 1 bit, and if I want to design for 2 bits, then I will require 2 flip-flops, right? And the number of states are decided by the formula 2 raised to n, where n is your number of bits. Okay, so if number of bits are 2, that is 2 raised to 2, then number of states will be 4. Okay, so number of states will be 4. Then now, for this type of a counter, number of flip-flops required are 2. As I have said, flip-flops required are 2. So to design it, now to design any flip-flop, first which type of flip-flop you will use. So we have studied different types of flip-flop like SR flip-flop, then D flip-flop, T flip-flop, and JK flip-flop. Okay. Now, which flip-flop we are going to use? In For the counter application, always we prefer a T flip-flop or a JK flip-flop. Okay, we always prefer T or JK. Why? Because in T and JK flip-flop, we have one mode which is called as a toggle mode. And what is this toggle mode? In this toggle mode, for a clock pulse, for any clock pulse, we get output in a toggle means if the previous state output is 0, you will get in the next state as a 1. If in a previous state output is 1, in the next state you will get it as a 0. Means your output will get toggled always. And it is possible only in a JK and a T flip-flop. And what a counter is? Counter application is actually just changing one. For each clock pulse, your count will get either incremented or either it will get decremented for each clock pulse. And whenever we are getting a count either incremented or decremented, there is only a change of 1 bit. Okay, and to get a change of 1 bit, to toggle that 1 bit, the toggle flip-flop or a JK flip-flop is used. Okay, so for 2-bit asynchronous counter, what is the structure or how the circuitry is that I will show. We will design it by using a JK flip-flop. Okay, as I have told you, we can either use a JK or a T flip-flop. Now, these are two flip-flops I am using. I will call it as a and B flip-flop. Okay, so JA, KA with the output QA, JB, KB with output QB. Okay, and both these flip-flop are negative edge triggered flip-flop. So what is negative edge triggered flip-flop? It can be either positive edge trigger or negative edge trigger. Okay, in a negative edge trigger means if there is a clock cycle, if this is a clock cycle, this is a negative edge means which goes from high to low, and the edge which rises from low to high is a positive edge. So for each clock pulse of a negative edge, your flip-flop will get triggered. Okay. So as this is a asynchronous flip-flop, clock will be provided to your first flip-flop, while the clock for second will be provided from the output of previous flip-flop. Okay? And as I have told you, we are going to use J and K flip-flop in a toggle mode. For that, we need to connect this J and K flip-flop permanently to VCC, because permanently we are going to toggle it for each clock pulse. Okay, so this is a simple connection diagram. We will just get this output QA and QB. Okay, so and always remember one important point, that the clock is provided always to a LSB bit of your counter or LSB bit. Okay, and so QA will be your LSB, while QB will be your LSB. Okay, now if, as I have said, QB is your MSB and QA is your LSB, right? So in the previous state and the next state, now how will be your state table? This will be your previous state, and this will be your next. Okay, 0. In the next state, it should be 1. For 0, 1, it should be 1, 0. For 1, 0, it should be 1, 1. And for 1, 1, it should be again 0, 0. Okay, in this way, actually, your counter should work. And if you will observe, the count is going from, you will observe the count is 0, 1, 2, and 3. Means this is actually a up counter. Sorry. I have written down. So this is actually a up counter. Just a minute. Okay. Now how does it work? So we will see with the timing diagram. Now, as this is a negative HTML program, okay, so I will draw here how the big changes. I will just write here your QB, QA, 0, 0. Okay, so I will draw the clock cycle. Okay, then here I will write QA and why I'm writing here QA and QB. This is your QA is your MSC. Just a minute. So QA is your MSC, QB is your MSC. So as in our diagram, if you have seen in the diagram that where is our QA? The clock is provided to QA and QB will change as per the change in QA. Okay. So on the basis of clock edges, negative clock edges, which output will change? QA output. Okay. So on each of these clock edge, this is negative clock edge, right? Sorry. Negative clock edge means from high to low. So this is first, second, and this is your. So this is your first clock edge, second negative clock edge, and this will be your third. So at this each pulse, negative pulse, your output QA should change, right? So initially, okay, so initially your QA is 0, right? Your QA is initially 0. So make it as 0 first. Now, at this clock pulse, as I have said, your QA will get toggled from 0 to 1 and it will remain same till the next clock pulse, next negative clock pulse. At the second clock pulse, so for the first clock pulse, your QA will be initially 0, and as soon as your clock pulse is first, at that time your QA will change from 0 to 1 at the first negative edge of the clock pulse, while your QB will remain 0 only. So your QB will remain. Okay. Now for the second clock pulse, see, for the second clock pulse, again your QA will get toggled. So as it was 1, it will get to 0 and it will remain 0 till the next negative edge clock pulse. Okay. Now here, so for the second clock pulse, here this will be 0. Now, what about QB? When your QB will get activated, when your second flip-flop will get activated for the negative edge of QA. Now, for the negative edge of QA means, which will be a negative edge of QA? This one. This one will be negative edge for the QA, and this negative edge, okay. Now, this negative edge of QA, just a minute. This will be the negative edge of QA. Means when your QA will go from 1 to 0, this will act as a negative edge for B flip-flop. And at that time, your B flip-flop output will get toggled and it will change from 0 to 1. Okay. So at this point, you will get output and it will get changed from 0 to 1. So as it was 0 initially, now it will change to 1. So see at this clock you will get it as a 1. Okay. So now it will change from 0 to 1. Okay. Now third clock phase. At this third clock phase, again QA will change from 0 to 1. Now this will remain 1 only. And when this at the fourth clock pulse here, that is fourth clock pulse, this will get again 0 and this will act as a negative clock edge for your B flip-flop and it will change from 1 to 0. So this will be 1, this will be 1, and at this stage it will be again 0 and this will be 0. So if you will observe, this state is your 0 0 state, this state is 0 1, as this is your MSB bit, this is your LSB bit, this state is 1 0 and in this state it is 1. Is it clear? And this repeats and this repeats for after each of this cycle. Is it clear? So in this way your counter works. So this is a best example, or in this way we are able to design and explain the up counter. Okay. So this is a 2-bit up counter. Similarly, you can design a 3-bit up counter. Okay. So here, if you will see, this is the state table and this is the state diagram for the up counter, 2-bit up counter. Similarly, you can design a 3-bit up counter. Okay, so this is a asynchronous counter. For any query, you can contact me. Thank you.